Everyone, in this video I'd like to talk about loop invariants. The reason that we have loop invariants is because it's kind of hard to keep track of what is happening with loops. Sometimes loops don't terminate or they terminate without achieving their goal, and that's a common problem in computer programming. Loop invariants are going to help. So what are they? Loop invariants are a way to reason about the correctness of the program. And more specifically, a loop invariant is a Boolean predicate that is true directly before the loop executes, that is true before and after each repetition of the loop body, and that is kept true directly after the loop has executed. In other words, it is kept invariant by the loop. It doesn't vary, it doesn't change, so it is invariant. Before we go into looking at a loop example, let's dial it down to just this following code snippet. Int x is equal to 0 and x is equal to x plus 1. If you run this code, you can actually reason through what things are true at any given state. So before I went into that statement, x is equal to x plus 1, I already knew that x was greater than or equal to 0. That was basically this statement here. Because I'm after int x is equal to 0, I know that if I did this check right here, it would tell me that that was true. And similarly, if I check after the x is equal to x plus 1, that same thing is going to be true because I added 1. So in this case, I've looked at something which is true before the statement executes and something which is true after the statement executes. So good, this is true reasoning. I know that x is greater than or equal to 0 as a precondition and as a postcondition. You could, if you weren't thinking too hard about things, you might say, oh, at the beginning I have x is greater than or equal to 0, but then at the end I think x is equal to 0 for some reason. And basically, if you don't reason correctly, you might come up with some sort of false precondition or false postcondition, which means your program is not going to do what you think it's going to do because there's a problem with your logic. Now, for something so small like this, it's unlikely to have these kinds of bad reasonings, or it's less likely, but with loops, it gets a little bit trickier. So let's take a look at a while loop example and see how we can reason through what's true before and after each iteration. So a while loop would kind of look like this in code. You have some initialization and then while b s. And now I'm going to talk about this new thing called an invariant p, which I'll talk about in a second. B is the loop guard and s is the statement. So if you draw this as a control flow diagram, it'll look something like this. And so now I have this p invariant that I'm reasoning about that is going to be true when we go into the loop for the first time. And basically, since I want p to be true before and after each iteration, it's going to p is going to be true after s executes, and then again as you go into b. And then at the end, when the loop terminates, p will still be true. When the loop terminates, p will be true, but b will be false. Because p was a loop invariant, it was true before and after each iteration, but you only go into the loop if b is true. Okay, this is still a little bit abstract, so let's look at an example. So let's look at this example where I want to do some exponentiation. So I want to do b to the c. And my requirement for this method is going to be c is greater than or equal to 0. And basically, it's just exponentiation for integers. So I've written an if-else here, where if c is equal to 0, then I'm just going to return 1. And in fact, it is true that b to the 0 is equal to 1. So in fact, that is b to the c. So that works out. And on the other hand, if c is greater than 0, I'm going to set the answer to be math.pow bc. And if you believe math.pow works the way that it should, then this will give you the correct answer. I also made sure to cast to int. Good. So basically, I know that if c is greater than or equal to 0 at the beginning, then my answer is going to be b to the c before the return. I've guaranteed that with each of the possible paths that you can take through this decision diamond, right? So either the if is true, it's c is equal to 0, or the if is false, c is greater than 0. Good. Let's look at a slightly different version of this same problem. So it does the same thing, only I've written an extra set of ifs here. I have if c is equal to 0 and if c is equal to 1. If c is equal to 0, ans is going to be equal to 1, and if c is equal to 1, then ans is equal to b. And if you reason through here, you'll see, yeah, well, when you have b to the 0, then the answer should be 1. And if c is equal to 1, then, well, it's b to the 1, so the answer should be b. So that works out. And then the last precondition that I'm looking at, because I've taken care of the case where c is equal to 0 and c is equal to 1, I need to look at c greater than 1. And so that's down here in my else block, which I've done b times math.pow of b comma c minus 1. And again, if you believe that math.pow works the way that it should, then this will give me a correct answer. So as you can see, at the beginning of each if statement, there's some requirement to even get into that if in the first place. I basically just rewrote what the if statement had. And these are what I would consider the preconditions for each of my ifs. And then, because that's true, then when I am done with that particular if block, I know that I'm going to have answer is equal to b to the c. And since that's true on each possible path that I can take, I believe that overall, my program is going to give me b to the c. The reason I bothered with those if statements in the first place was to build the example slowly. And so now I have a for loop. And you can kind of see how I've gone from having a sequence of if statements to having a for loop, where basically I have int I is equal to 1. So at the very first check, I have I is equal to 1, which means, in fact, I is less than or equal to c. So that's true. And then I continues to grow, 2, 3, and so on until it actually hits c. And I know there that I is less than or equal to c. So I could have a sequence of if statements to this effect right here if I wanted instead. That's my test. But I'm not going to test these, I'm not going to write c many if statements, so instead I have this for loop. And let's just follow what's going on in this for loop. I've set first ans is equal to 1, and then inside the loop, I have this rule that I is less than or equal to c, and the ans is equal to b to the I minus 1. And if I loop through, I see that I'm going to do ans is equal to b times ans, and that's how exponentiation works. And at the end of each of these iterations, I will still have that b to the I minus 1. Ans is equal to b to the I minus 1. The reason that that is held true is because of this I plus plus here. And at the very end, it's going to actually be the case that I is going to be equal to c plus 1. That is where the loop guard fails, and I is not less than or equal to c. So in this case, you don't enter the loop, but the loop invariant is still true. And in fact, I can conclude that ans is equal to b to the c. Let's look at this example a little bit more. To help out with scoping, I've just rewritten this for loop a little bit. It's going to work the same, but this helps to see what's going on with I. I've set int I is equal to 1 outside of the loop, so the scope of I is outside the for loop. And if you look right here, depends on what c is, but it should be the case that to go into the loop, that I is less than or equal to c. So c is equal to 1 or greater. And if that is the case, by the way, the answer so far is equal to b to the I minus 1 because this is currently b to the 0, which is in fact 1. So that's true. And now I'm going to do the loop exactly the same. And here's where I want to show you how the loop invariant is going to be held true. I'm going to show you with the debugger. Okay, so here I have in VS Code just me showing what the code would look like, and I have a main here that's going to call x of 2, 3, and let's go ahead and debug Java to see what's going to happen, and I'm just going to step through. So when I call the method, b is equal to 2 and c is equal to 3, and I'm going to step into the code. I see that ants is 1, and I is 1. And the first time through the loop, I is equal to 1 and c is equal to 3. So let's keep going. Ants is equal to 1, b is equal to 2. So at this point, when the loop is done, you should see that I is equal to 2 and b is equal to 2 here as well. And so we can see that b, ants is equal to b to the I minus 1. Good, so let's keep going. And each time you're looping through, at this point I is equal to 3, so this is still a true for loop, and we are going to enter. But at the last iteration, we're going to be done. And the only reason, by the way, that in my debugger I can see that the final value of I is equal to 4 is because I declared I outside of the for loop in the first place. But I do see that I is equal to 4, which is c plus 1 in this case, and my answer is equal to 8. So it did give me the right answer. So now, hopefully with this debugger, you can kind of see how throughout we had ants is equal to b to the I minus 1 before and after the loop. Sometimes during the statement of the loop, it would not be true. But at the very end, because it's true before and after each loop, at the very end, we get the answer that we wanted. So the point of all that was that combined with the loop guard, or the loop condition, the loop invariant allows us to reason about the behavior of the loop. And so in general, the code structure will look like this. You have a loop invariant, something that you know is true before you go into your loop. You have some tests. Inside your loop, at the beginning, you know the test and the loop invariant is true. Then you have your loop body, and then at the end, the loop invariant will be true again. At the end of the while loop, basically you don't go inside again because that's the place where the test is not true and the loop invariant is true. So we saw this before with the control flow diagram, but here's just another way of writing it. And so remember, I had the test was the loop guard, which was B, so I was saying not B, but I have P, the loop invariant, still being true. And basically, if you can prove to yourself that the loop invariant holds before the loop and that the loop body keeps the invariant true, then you know that at the very end, when the loop terminates, that the test is not true, but the loop invariant is true. And that is how you decide whether your loop did the thing that you wanted it to do. One of the reasons that you might care about doing loop invariants is because you want to write a loop to go over and iterate through an array to do something. Many loops do process elements of an array B or a string, or really any sort of list in order. So we often see B of 0, B of 1, B of 2, and so on. When you have this invariant then, basically you can think of it as the part of the array B that's been processed, and then the part of B that's not been processed. So if the post condition is specifically, I want the whole array from 0 to length -1 to have been processed, then at the beginning, nothing has been processed. So there's not really a way to write this in Java, but nothing has happened. And then after k iterations, k elements have been processed. In other words, B of 0 up to B of k -1 has been processed. So let's say that your overall task is to process an array from B at 0 to B at B.length -1. when you want to write your loop invariant, you basically replace b.length in the post condition by a fresh variable k to get the invariant that b at 0 up to b at k minus 1 has been processed. Let's actually look at some pseudocode to see what that means. So I'm going to write k is equal to 0, and then as long as k is not equal to b.length, I'm going to have this ability to process b at k. I don't know what that means in as a specific piece of code, but I'm going to do something at b at k. And k is going to be equal to k plus 1. So at the end of each iteration, because I processed b at k and then k was updated to be k plus 1, I can guarantee that b of 0 up to b at k minus 1 has been processed. And that's basically all you really have to say when you're doing this sort of reasoning about arrays. Okay, so let's look at an actual piece of code where I'm basically just going to create an array that is going to take up the values from another array. So here's b, and it's going to take the shift. So it's going to, instead of being, so a is equal to 1, 2, 3, 4, 5, and I think b should be 2, 3, 4, 5. Okay, so in this case, we are wanting to process b, and so I'm going to go through this loop while I is less than n minus 1. So at first I is equal to 0, and now I'm going to update the b array to shift elements. And you're going to see right here that b of 0 has been processed, b of 1 has been processed, depending on where you are in the loop, all the way up to b at I. And then I gets incremented. So because I got incremented, we can now guarantee that b 0 up to b I minus 1 has been processed. And another way to write this is for all, so I just introduced a new variable for all j. J is between 0 inclusive and 1, and I not inclusive. B at j is equal to a at j plus 1. And so this is these two things are kind of equivalent ways of talking. And then because that's true all throughout my loop, at the very end, I have I is going to be equal to n minus 1, right? Because that's what broke me out of the loop. And so now I know that for all j, 0 is less than or equal to j is less than n minus 1, b at j is equal to a at j plus 1. Or again, the other way to write it is b at 0, b at 1, and all the way up to b at n minus 2 are all individually equal to a at 1, a at 2, all the way up to a at n minus 1. And so that works out the way that we would kind of like it to. So good. With this example, I hope to have clarified what sorts of invariants we're looking at with arrays, although I do recommend you type this up and try a couple of different values for n and a and b and see what's going to happen. Loop invariants are also really helpful towards tracing loops. So you can start building out a table of what the iteration is and then what the values of the numbers or any variables are in that loop. So I kind of did this with the debugger with a different example, but this is the one that I'm going to leave you with. It's a partially filled out table of this particular piece of code right here. And I highly recommend you think about what's going to be true at the beginning and end of each iteration of the loop and what the whether this table makes sense and whether any more values in the table need to be filled out, and figure out what's going to be printed out at the end. So that's all I have for this particular video. Thanks for watching, and please let me know if you have any questions.